Good morning, everyone. Welcome to Automation Alley's virtual tech takeover. I'm Seta Sykes, Automation Alley's account manager. This tech takeover is brought to you by one of our foundation members, Manpower Group. Manpower Group provides administrative and support services, professional services, and business services through its four primary brands: Manpower, contingent staffing and permanent recruitment; Experience, professional resourcing and project-based solutions; Right Management, career management, workforce consulting, and training and development; and Manpower Group Solutions, managed services and outsourcing. If you have any questions regarding Manpower or any of their services, I'll be more than happy to connect you with a representative. Information can also be found on the Tech Takeover information page. Every Wednesday, we host these member led Industry 4.0 focus sessions via live stream. This week's topic is Join the Additive Manufacturing Transformation with Tata Technologies. I'm pleased to be joined this morning by our speakers today: Chris Weber, the Director of Additive Manufacturing Solutions, Siemens Digital Industry Software; Steve Sleeger, Siemens Product Manager, Tata Technologies. Casey Pratt was scheduled to be our original speaker this morning, but unfortunately is unable to make it today due to personal reasons. We'll be doing a Q&A sessions at the end of today's presentation, so please use the Q&A function at the bottom of your screen. Thank you. I'd like to now welcome our panelists.
Hello, I'm Steve Sliger. I'll be doing just the brief intro and end. Chris Weber from Siemens will be doing most of the conversation. So, Chris, you want to introduce yourself?
Sure. Hi, Steve. Long time no speak. So I'm Chris Weber. I'm responsible for our additive manufacturing software portfolio for the Americas for Siemens. So I work very closely with the other sister organizations within Siemens. We work together with our motion controls and factory automation side of the house and our corporate technologies, which is our R&D center, as well as robotics. And so we have a lot of knowledge and expertise within Siemens that when we go after additive, we come at it, as one Siemens.
Thank you, Chris. So we'd like to welcome you to this Automation Alley webinar. What we're trying to do is introduce a lot of the advanced topics around additive manufacturing and help you transform. So there's the industry is evolving quite quickly, and we'd like to take you down that journey. Let's see what's going on here. So this is just a generic slide from Tata. We have Tech Talk Tuesdays every once a month, and these webinars are at 1 o'clock every Tuesday. The topics vary from NX CAD to NX CAM, Team Center, FEMAP, Sim Center, and Technomatics. We always use Zoom to deliver these webinars. We asked that in this case we put the questions in the Q&A window, not the chat window, and we'll enter and answer all the questions at the end of the session. So thank you for joining. We are a platinum level partner, smart expert in NX CAD, NX CAM, and FEMAP and Sim Center. So we've been a partner for well over 20 years with Siemens, and we provide both training, support, and just about any needs that you have around technology. Okay, Chris, I'll stop sharing.
Okay. Now let's see if I can pick up my share here. Okay, hopefully, are you seeing the notes or are you seeing the?
Flip the view, yeah.
There we go. Beautiful.
Yep,
okay.
We're good.
All right. So again, good morning. I'm Chris Weber. So I'm pretty excited and fired up to be here this morning. So so in talking with Steve, trying to figure out, how much of additive and what to cover. since there is so much. I mean, we could definitely talk the entire day about additive. And if anybody knows me, I really could speak all day about additive. I've been in manufacturing, coming up on 35 years. So I have in some shape or fashion have been involved with startups for some reason, my whole career, going all the way back to General Motors, working on the Buick Reatta program and getting that launched off the ground. And that seems to have been kind of the theme for my whole career. I did have experience with additive back in the late 80s, early 90s with stereolithography, what I used to love to call the potato chip models. They were so fragile you didn't want anybody to sneeze in the room because you'd blow the models apart. So it's come a long way since then. Even that type of technology using polymers has improved drastically, and those parts can be used also for end use. So again, it's come a long way. And so I came back into the role or for additive to lead this activity for the Americas. It's almost been 4 years now, and it's been absolutely exciting. And the neat thing about this is if you look over the last 100 years, there really hasn't been a technology that's been so transformative. Um, so even when you're talking about metal forming, hydroforming came out, for instance, and it was just another version of metal forming. It wasn't anything that was going to rock the world, so to speak, right? And so those type of technologies are are few and far between, really. And so and where we are generally, just as it's, which is pretty interesting from my viewpoint, is whether you're a printer OEM, whether you're a materials manufacturer, whether you're a software developer or an end user, we all seem to be on this far left-hand side of innovation and development. So if you look at a typical product life cycle, very few people in those categories are really in this repeatability process and getting into more of a mature life cycle because things are changing. Even some of the standard technologies that are out there, people are coming up with different ways of leveraging lasers and the number of lasers and controlling the lasers and different types of materials. So we're working with one materials company that's come up with a way to make perfectly spherical particles, right? And so that helps with conformity and repeatability. So it's extremely exciting and a little bit tongue in cheek for our executives on the Siemens side. On the early on, it was kind of funny because some people's like, well, how hard can this be? It's just like printing on a sheet of paper, right? I mean, it's printing. Come on. So I had to, I created a slide that had the Starship Enterprise leaving the orbit of the Earth. And so that was kind of my mantra is we're going where no one's gone before, right? So we think we know some things that are out there or we'd like to be with additive, but we're at the forefront, right? So is it going to be a panacea and replace, all sorts of or types of traditional manufacturing? Not in my lifetime, that's for sure. But that it does give us some different opportunities in the engineering and the manufacturing side of the house that we didn't have before. So again, just based on not knowing the maturity of additive out in the audience, so I thought what would be best is maybe to give a little taste of different pieces of that, and hopefully that'll either answer some questions for you, or even more importantly, generate a lot more questions that you'll have, and as you go down this journey. So what is additive manufacturing, right? We're all familiar with machining, or at least most of us, right? Which is considered subtracting. We're taking away material. So we're taking a block of a material and then we're cutting it into a shape. Whereas on additive, The reason why it's so innovative is you're actually building up the material. You still may be doing some type of subtractive to it if you're talking about metals, but for the most part, we're really focused in on growing a part. That's probably the best way to look at it, growing a part. And when you grow a part from a design perspective, that gives you a whole bunch of um, degrees of design freedom that we didn't have before. Things like being able to put cooling channels right within walls. That's something that you just can't machine, especially if you have a complex shape. You might be able to machine something with a cooling channel if it was straight, right? But if the wall's really thin, that's preventative. It's really hard to actually machine something like that. And then as soon as you start getting into convex, concave shapes, where it's taking twists and turns, then it's impossible to do that. So think about additive again is you're growing apart, right? And it's giving you some degrees of design and manufacturing freedom that traditional manufacturing wouldn't be able to give you. So why would anybody go down the path of additive, right? So as I mentioned, the design and the manufacturing side of the house. So from the design side, maybe you're trying to get better performance out of a part, right? A heat exchanger is a really good example, right? If I can make a heat exchanger smaller and package it, in a different way than I could, whether it's in automotive, right, or maybe even racing, right, or aerospace and defense, where those are all areas where packaging makes a huge difference. And if you can make something smaller and lighter, but perform even better, either the same or better, then that's a positive, right? Design complexity. As I mentioned, being able to put like cooling channels within the thin walls of a part. So the higher degree of complexity that you get with a part, that kind of lends itself more towards additive. Weight, again, in automotive and aerospace and defense, weight is a big factor, right? We all know that. And so if you can make something lighter and still be as strong or even stronger, and that's a positive, right? Those are things that using lattice structures, for instance. So you're removing a lot of the excess material that you really don't need, but you're putting the material where structurally really is important to have. Material properties is another one, right? Speed to innovation. We all pretty much are familiar with prototyping. Prototyping's been around for a long time. So to be able to iterate on a design faster is important. We have some consumer goods customers that they do a lot of prototyping for clinics, right? So think about if you're doing I don't know, toasters or blenders or vacuum cleaners or whatever, right? If you can bring people in and have him try out the product, how does this button feel? How's the handle feel? Is it ergonomically correct? Should the handle be a little thicker? Should it have better grips? Right? They can give the feedback, and then literally within 24 hours, depending on whatever you're printing and the material you're using that, but with a 24 hours, 48 hours, you could have a replacement part for that and bring those people back into a clinic and actually say, okay, we took your feedback into consideration. What do you think now? Right? So just in prototyping in itself, that allows you to do those iterations much faster, because let's say it was plastics. To be able to make that change, you'd have to create another mold, right? That takes time and that takes money. So speed of innovation is really important. On the manufacturing side, lead time is a big deal. With COVID, a number of companies have figured out that the supply chain disruption is a big problem, right? Especially if you're relying on somebody that you've outsourced to Asia Pacific, for instance, right? Well, everything's shut down. It's going to be a while. We don't know when you're going to be able to get your parts, right? So Some of our customers are actually utilizing some of the technologies to create what I would call a dirty forging or a dirty casting. You're going to machine the part anyways. So you print something that is relatively the rough shape of what you want, and then machine it. And that's cut out that whole supply chain on the front end. Again, the next thing is kind of related to this. What I would say is cost is a factor, obviously. It might not make sense, especially metal forming is pretty darn cheap, right? If I have to stamp some parts. So if I need a million of a certain bracket, I'm probably not going to print those additively. I might down the road for a spare part, but I wouldn't use it for production. So cost, the economics is always a factor. You always have to think about how many am I going to make? When do I need it? What materials am I going to use? Right? And those factors may change because I may decide to make something additively. It may not be a design consideration, but I just, I want to get my product out there. I might make it additively, and because I only need, let's say, 500. But then let's say the product takes off, and as long as I can still, let's say, machine it, then if the need goes up to 500,000, then I may decide to change that design. And as long as I'm still within spec, I may go to machining that part. So the cost is always important, right? So cost is always a consideration of when and how you decide to do additive. Quality is also a big factor. So one of the things that we don't have is standards within additive at this point, like we do in all the other modalities or technologies, types of traditional manufacturing. So those standards have yet to be developed. So ensuring repeatability and first time right is a little bit more difficult, but again, it depends on the materials that you're going to be using and the type of technology. Serviceability, that's another area that you may decide to do additive. I think I mentioned, right, maybe in the spare part scenario, or maybe a tool. Maybe you as a company have a piece of equipment that's been out there since the 1950s, and it breaks down. You don't have the prints. You're going to have to do some type of scanning and reverse engineering in order to reproduce that part because it's still a viable part. I mean, we have that scenario with our B-52 bombers, right? They're still in the air, but a lot of those suppliers have gone out of business. Who knows where the prints are? So you would have to take a good part or a relatively good part and scan it in, and then reproduce that part, and then you'd have the geometry for the future. And it's the same thing when it goes to inventory spare parts in the shop floor. If you think about how many spare parts that are in the spare parts stores in a manufacturing facility, and you multiply that by the holding cost, it can get into multiple millions. And so what if you thought about your spare parts to say, which ones could I print on site, right? So I'd have to really investigate how often do I replace that part? How much does the part wear? What's the mean time to failure, right? And I might be able to say, it'd be really good to have a printer on site for some plastic parts that I don't have to house because they've been sitting there taking up, collecting dust or making it out of some type of composite. So inventory is another big area, and there's going to be another area of growth of trying to reduce the amount of spare parts that you store in your manufacturing facilities. And we all know that space costs money. So if we reduce the amount of space, that's money back in our pocket. So the whole idea of additive hits a number of areas, right? One is reimagining parts, right, or your products. combining parts, maybe an assembly that was made up of 12 parts, and you redesign it into one part and make it more efficient. So it really allows you to think out of the box, whether it's a part, whether it's tooling, fixtures, molds, redesigning a mold, for instance, to be more efficient so that it actually cools faster and I can get more parts out of the mold per hour. So you really, you can't limit yourself, right? As far as additive, it allows you to think out of the box and look at each type of pieces of business that I have, whether it's on the small scale, looking at, I have a particular problem and I need a hammer for this nail, to I have an enterprise problem, which is like the spare parts is a good example, right? Spare parts. I have an enterprise problem. How can additive help me alleviate or reduce the amount of costs that I have for spare parts, right? And that falls into rethinking, your business, individualization, personalization. We're starting to see that in the automotive area, right? But those are on limited production vehicles, for instance. Where you can personalize, components inside the interior, for instance. Even getting to the point where, and that would be way out in the future, imagine having zero inventory, right? Imagine the implications on taxes, right? Because you have no in-process or finished goods sitting around in the plant. You're going to make them when you need them, right? On demand. So that's going to have an effect on global trade, being able to design anywhere, print anywhere, right? So some of those barriers start to come down. And then also when we think about reinventing manufacturing, think about for anybody that's in automotive, we have body in white, right? So we have a line where we have a welding operation, welding up the side frames of the vehicles and creating the structure, right? The base structure before it goes into the paint shop. How about body in black, right? You still have the same robots, but you're using carbon fiber, for instance, and now you're growing the car body instead of welding up panels. So it again, it's really allowing us to rethink our products, our process, the tools that we use as part of the process. And so this is what makes it so transformative. So it's not just, again, just from the engineering side, but also on the manufacturing side also. So where do you start, right? So this is kind of the conventional thought, right? So when we look at a lot of companies started out with prototyping. So again, prototyping has been around since late 80s, early 90s-ish, and has continued to grow. That still predominantly is the most usage of additive. There's about 80% of all folks using additive are using it for prototyping. And then also for tooling and fixturing out on the shop floor. So those are pretty easy ways to get into additive, quite frankly. But that doesn't have to be that way, right? So I've been with customers that have jumped in all over the place. Some just dive right in for design for additive. Some are looking at part replacement, reverse engineering. Some do part consolidation. So there's many different tactics that you can employ as part of your overall strategy. And that is one of the key things that I really want to make sure that everybody understands, is that you need to have a strategy for additive. Best is to have a corporate strategy for additive. You don't want to just go and buy a printer just because, as I like to say, wow, all the cool kids have one on the block, so we should have one too. And you have no idea why you're buying it. You have no idea what you're going to do with it, and it's just, you're wasting your time and your energy. So there's so much information now out there, and there's so many folks that can help you with making that decision on what your strategy should be. That you really shouldn't be in that scenario where you just decide, well, we'll just buy one and then we'll start, we'll figure it out from there. It's really not a good strategy. So really decide for yourselves. Again, if you're not doing prototyping, should we do prototyping? Do we do fixtures maybe, right? Those are quick and dirty type of things, and it's very economical. And as the fixture wears, it's a throwaway. So really think about what that is. And the other thing is too, is make sure that everyone else knows within your company, within your enterprise, of what you're doing. There's been a number of customers that I've talked to where, I've talked to the manufacturing engineering organization, and they're like, oh, what should we do? Where should we start? What materials should we be using? What printers are the best printers? And I've made a comment to say, well, your engineering organization has a bunch of printers just down the hall. Have you talked to them, or have you leveraged some of their printers? Nope. No, we haven't had any conversations with them. That's crazy, right? But it happens. So always have a strategy, right? Or come up with a strategy and where you think for your company, you're going to get the biggest bang for your buck, right? And to be able to grow your resources, because the knowledge for this technology, they're not just all lying around on the street looking for a job, right? This is a very hot area, and maybe some of you already have experienced trying to find, hire people away. It's pretty expensive, right? So you're going to have to also invest and grow your people. So just like you're growing parts, you want to grow your people. So from a Siemens side of the house, why are we doing it, right? Well, Siemens makes industrialized products. So for us, we're selfish, and we know that additive is going to provide us capabilities that we can't get elsewhere through traditional manufacturing. So we've invested in our business units. So as you see in power generation, you see these fan blades, power services. So the maintenance side, so we have turbines that are out in the field, whether they're naturally gas fired or steam turbines, and the money is in the maintenance contracts. So the more your turbine goes down, the less money you make. So that's important. Mobility, the high-speed trains. We're using that. I've got some examples of these here as success stories, but we're using it in the mobility services. Healthineers, our healthcare side of the house. Things like cutting guides for surgeries, right? The software side of the house, where I'm from, is creating the software that enables the design and the validation and the printing and the feedback mechanism or loop in managing that whole process. Motion controls, right? So we're working with the printer OEMs to outfit these printers with proper controls, because at the end of the day, if you're going to be serious about production, those printers have to be industrialized and they have to play nice on the factory floor. You can't afford as a company to have some architecture that's like way out of whack from everything else, right? So that's important, the motion control side of the house. The corporate technologies, I think I mentioned earlier, that's our research and development. We have a high degree of specialty knowledge within additive, and doing a lot of advanced approaches and methodologies and software for additive, as well as we have metallurgists in our Charlotte facility that are actually doing validation and things for some of the printer OEMs for the powders that's being used. So doing a lot there. And then material solutions is our service bureau side of the house. So we have a number of locations around the globe, our largest being in Worcester in the UK. And we opened up one in Orlando about a year and a half ago. And we predominantly utilize powdered metals there. So we have a lot of areas of focus within the company. So that's why it's important for us. And I'll cover some of the success stories there. We also have we call our Amec, our Additive Manufacturing Experience Center, that we opened up last year in 2019. And so we have a facility there in Erlangen, Germany, which has a representation of all the different printer modalities. And we can bring customers in to do workshops and clinics and that to get hands-on with with the software, with the printers, with the materials. And then we have a center, kind of a satellite of this that we're opening up, hopefully, with the whole COVID stuff, I would say June, July-ish of next year, in our Charlotte, North Carolina facility. So similar type of things where we'll be able to bring customers in to get some hands-on, some maybe some design clinics. If you're not certain about a specific printer modality or material, to be able to go in again and get some hands-on. So we're really excited about that. And we also have a digital version of this that we opened up in February, and a lot of that was due to COVID. So we can go through a whole walkthrough in a virtual environment of the Erlangen facility, which is really cool. So we've gotten a lot of feedback from customers that they really enjoy and appreciate that also. And then I mentioned our service bureau business. So we have roughly 40 EOS printers predominantly. I think might have a couple of Renaissance in Worcester, and then here in Orlando, we started out with a couple EOS printers, as well as I think there may be a Renaissance on the way also. So we can we can print parts not only for ourselves there, which is predominantly what we do, but we do spend, I think, 20% for outside of our business as well. One of the things that's very unique. So from the software side, we're well known for managing the entire process from ideation through the validation of the design, as well as the manufacturing planning and validation for that, and virtual commissioning, and then all the way out to the shop floor. And so one of the things that we are focused in on is, additive is special, but it isn't that special that you want to treat it like an island. It has to play nice with the rest of traditional manufacturing. So it's not, again, a panacea where you're going to junk everything that you have on a traditional basis. Everything has its place, right? Because it'd be completely insane to say that, well, I'm going to print hoods. No, that doesn't make any sense, right? So it has a place. And so our big thing is that we have incorporated the additive.
Hey, Chris, I think your Bluetooth went down.
Hopefully everybody.
Chris, we can't hear you.
Can you hear me now?
Yeah, it's good.
Okay. Sorry, my Bluetooth went out. So we've incorporated, the whole approach for additive, that it has to be a part of traditional, or play with traditional manufacturing. So that's important. So we want to treat it, handle it, enforce it in a way to play nice. Right. So again, you can't afford to have a new technology like this, especially if you're trying to productionize it, sitting off in its own little island. And the other thing that's different too is with our motion controls factory automation side of the house is we're working in partnership with a lot of the printer OEMs. So we're outfitting some of those with our controls, which I'll cover here in a little bit. But that's important too. And there's some inherent value that we get in utilizing, for those of you that may have Siemens controls, that there's some Easter eggs that are available in utilizing our NX software.
so that you can actually do a simulation and validation of the process and then be able to capture that data. So that's an important factor. So we're not only just looking at the process, but we're extending that back up into the printer OEMs. When we look at the process, so those of you who already have been in this space, for those who haven't, it's a pretty chopped up process. Again, we didn't put a lot of emphasis early on from a software focus. Full disclosure, back in the early days of prototyping. So what's being used out there is, sometimes people are using 3, 4, 5 different software packages. And if you're trying to get into the production side of the house, that becomes very limiting, and it opens up, yourself to error. And that's the last thing you want, right? Because we always want to do first time right, especially if we're talking production. We want first time right. So for us, again, taking the same approach that we do with traditional manufacturing, we bring that to the additive space. So what we want to do is we want to have a continuous workflow, right? So if you chose to, you could have one person just sitting at their their computer and going through the entire design, validation, and print prep and print process if they so chose to. And one of the key factors here is to be able to manage that. So PLM becomes really important. And that's, again, if you're not thinking about it, you need to think about it. Because if we're going to move, we, as all of us, right, in this additive community, if we're going to move additive into truly a productionized environment, you can't afford to have people walking around with the knowledge between their ears, or having, the secret sauce of how they know how to do a setup properly and support structures on their laptop. That isn't going to work, right? And for any of you that have gone to some of the industry events, whether it be AMUG or Rapid, or any of the other events that are out there, people talk about their successes up to a point, but they're not going to tell you the secret sauce. Why? Well, they don't want to give away the secret sauce, right? That's their competitive advantage. So it's going to be really important for every company to make sure that they're capturing that information, right? Capturing that knowledge. And so that the so-called formula is, as I keep referring to it, is, the being able to know when you're going to, if you can or can't reuse powder. Well, how much of the powder can I reuse? What is the best orientation for a part? What support structures work best? Do I have a way of doing a print where I don't have to cut so much off of a build plate if I'm doing powdered metals? So all those type of things. And then if you're going to print somewhere else, you need to understand what the conditions are. What's the environment where you got success, right? So where do you capture that? You really need to capture that. And for us, it's we're leveraging Team Center for that, is to be able to capture that recipe as part of an attribute with that particular part, so that when you go to print again, it's kind of like your setup sheet. What are all the things that I need in order to make sure I get a good part? And if I'm going to print that now in another country or a different location, that person needs to know, well, were those conditions, right? And you're still going to have to tweak, right? Because an M400 is not always an M400, because there's still a little bit of variation needs to be dialed in. But for the most part, you need to have a base recipe. And then when you go in the future, you look in the future, when you're taking on new parts, wouldn't it be great to be able to do a search to say, here's the key characteristics of this part. I want to do a search in the system to see what other parts like this have I successfully printed before, and how did I do the setup, right? Oh, these 3 parts. Okay, now I'm starting to learn, and I'm starting to move the ball, or move the needle, so to speak, right? Because I'm starting to work on collapsing that time to get my part printed and get to market, quite frankly. So that's what we have here. is basically, this is a particular workflow for powder bed metals, but, and this is assuming that you're going to create a new part. But depending on what printer modality that you're going to be using, right? Whether it's powder bed fusion, whether it's plastics for powder bed fusion, or if it's metals, is it multi-axis DED, directed energy deposition? There's things that you will do and you won't do, but this is kind of like a framework, right? Some instances you want to lightweight, some instances you might not want to lightweight. But that's pretty much the cadence is, you're going to have to come up with a way then to be able to go through the design aspects of it, in lightweighting. And the key thing is here is once you actually do a validation of the part structurally, right? You don't want to have to go back from a mesh into a solid and back and forth and do translations. With the way that we've architected the solution is you can continue in the whole process. So if there's an area where the walls need to be thickened up, for instance, you're not having to go and translate back into a solid. You can go all the way through the entire process, through the post-processing if you need to, utilizing the mesh. So that's our whole, convergent modeling perspective, so that you can do those iterations right then and there, and you're not having to go back and forth and do translations. So you can go through the whole process without doing any translations. And that's what's important if you're going to productionize additive. You can't afford to be going back and forth and in and out of packages and doing translations and end up with mistakes and errors and then having to clean up models. It just doesn't make sense. And again, even if you're running a prototype shop, right, and you're running it 24/7, that's a production environment. It's a production or lot size of 1 type of scenario probably, but it still has to run efficiently, and you can't afford to do that in jumping in and out of all sorts of packages. Doesn't make any sense. So just another view of the way that we look at, whether it's traditional manufacturing or it's additive manufacturing, is the digital twin is really important, right? So to be able to do everything in a virtual environment and have it representative of the physical. And for additive, that's exactly where we're focused and we continue to head, is that we always have a one-to-one relationship between the two. So that, again, you're shorting the overall design cycle, you're getting your products to market faster, and you're validating to make sure that when you print, it's first time right the first time you print. So just a few vignettes here. We're talking about virtual product. So creating a generative design and lightweighting structures, as well as adapting and optimizing the design, as I mentioned. So we're in the mesh here, and we're able to make changes, to the part where we see fit, and then doing the actual physical validation of the part, using CAE analysis, and then taking that information again, and then making those changes on the fly, and then doing a print check, right? So I want to be able to run a simulation on the print and validate and make sure that I don't have any areas of, where I'm going to have a fissure or a crack or deformation. As far as preparing, right, be able to have the build prep for the slicing and hatching, making sure that you're able to identify the proper support structures. We can do that automatically, or we can do that manually. Number of different ways that we can set up the support structures and make sure that we're positioning that properly. We can even, for the metals, the powdered metal side, we have a tool that we call the easy button, which can take somebody that's a newbie and act as if they're experienced. So it'll do the work for you in making sure it optimizes your orientation and the support structures. Predicting and compensating for thermal distortion, again, running the simulation then once you've positioned it and to validate that I'm not going to have any problems. And then I may need to go back again and maybe thicken up some areas or maybe create some support structures that will alleviate any areas of distortion. And then once I get to the point where if I have to do any type of post-processing, specifically here machining, is I already have that that data and I can machine right off of that data. So I'm not having to go through and then jumping into another package and then running a simulation. I'm doing this all off of the same CAD model. And then also the virtual inspection. So whether you're doing a in-process inspection or whether it's a standalone, CMM inspection, again, you have all the data available and it's all within, the same product within NX. And then the automation piece of this, the traceability. So in situ monitoring is really important, and especially when it comes to validating your assumptions on your simulation models, right? So what we assumed or theorized on what would happen to that model isn't in fact exactly what happened when we printed it, right? So the closed loop piece of this, utilizing MES and to be able to capture that data on the manufacturing process and be able to feed that back into the the overall cycle, development cycle of that part is key. And then also the improving machine quality. We have our totally integrated automation portfolio, which is all focused in on the shop floor, and connectivity with those printers. And then the production piece of this, the powder removal, an automated way of removing the powder, and then support structures, again, material handling, and whether you're doing that in a hybrid environment and removing some of the excess material, or whether you do that via, let's say in this picture here, a robot and machine it off. The other thing to take in consideration is if you're printing and designing in multiple locations, it can get pretty complex. So what we're trying to do is take away some of that complexity. And what we've done is we've created what we call our additive manufacturing network. That is a single source in order to do collaboration between an end user and supplier community. Whether it's internal, right? So your own internal service bureaus or an external service bureau, or other associates across other different locations. So we want to be able to have an exchange, if you will, in order to facilitate that collaboration as well as the bid process. So part qualification, collaboration, bidding, order management, part preparation, the planning and scheduling piece of this, which is really critical from a service bureau perspective, the execution, and then the reporting and the shipping, right? So those are all the things that we're taking consideration in with our additive manufacturing network. So what's trending? As I mentioned, there's a whole bunch of different technologies out there. 2 years ago, powder bed metal was the real big ticket. Everybody was focused in on that. There are some difficulties in with powder bed metals, and some people have decided to move away from that and look at some other technologies, binder jetting, or multi-axis, right? So multi-axis seems to be what I'm seeing, and this is me speaking, is in the last year, this is really starting to take off. Laser metal deposition, whether it's through powder or whether it's wire, arc welding, electron beam. Cold spray's been around a long time. It's been around, especially in aerospace and defense, since the 60s. but that seems to be making a big comeback, or at least a lot more push on it, especially for coatings. So there's a lot happening in the cold spray side of the house, as well as the material extrusion. So whether that is gantry based or whether it's robotic based, but that's another big area of growth. So multi-axis deposition, a lot of the OEMs, they're either, like as I mentioned on the previous slide, DED, which is directed energy deposition, electron beam, fused deposition, carbon fiber. That's another big one. The wide area additive manufacturing. So to be able to, think about a gantry in a warehouse where you could print a fuselage of an airplane, right? That's wide area. And then whether it's the head, the print head is mounted on a gantry, via CNC or robot. And so the benefits to that, strong post-processing capabilities, 5-axis capabilities is real important, and the user-defined events, as well as it's a natural fit, for us, being selfish again, for our cinemeric controls devices. So the CNC machines, there's hybrid, such as the DMG Mori, for instance, where you're doing additive and subtractive in the same space. And then, or if you're looking at just additive by itself, as well as some of the competitive benefits is high accuracy and rigidity, mixed manufacturing needs based on part requirements, right, at any time, reduced fixturing, and machine kinematics are well defined. So this is one of the areas that we're spending a lot of time and energy in. We do have a huge expertise in this area to begin with. And then just adding additive to it is just like adding another, option for us. As well as robotics, right? So the robotics is another area. So there are some OEMs out there that provide out of the box functionality for this type of technology, for multi-axis robot based, as well as we have customers that are coming to us saying that, hey, we figure we know robots, we know welding, we're going to make our own work cell. And so we're helping some of those customers, with designing those work cells. So this is a real interesting area. So I'm going to see there's going to be a lot of growth here. So this is one to really keep your eyes on. I've mentioned the workflow earlier. So as you can tell up here, that's basically the fixed plane or flatbed additive, as some people call it. That process is going to be different from multi-axis, right? So, for multi-axis, you're going to actually decompose the part, load the machine kinematics and locate part, whereas before you're going to be doing nesting. You're not going to do nesting in this scenario. The fixed plane, creating support structures. Here, you're actually going to be creating tool paths, right? Whereas before you would be looking at, slicing the data and doing post-processing. Here, you're going to simulate and post-process the actual tool path. And then the 3D print program is going to be different, because here you're actually going to run G-code to facilitate the print process. So there are some similarities with the process, but then there's definitely some differences in the way that you execute each of those components of the process. So let's talk about some success stories. The fennel bulb is just like one of our first ventures, and there's a kind of a cool story to this. So one of our engineers in corporate technologies was the first person that got the assignment that we want you to redesign a burner assembly that we use for our customers in a refinery. So, this gentleman decided, he couldn't really kind of think out of the box. So he ended up going to the grocery store and just happened to run across this fennel bulb, and, the light bulb went on. And that fennel bulb became the inspiration for the redesign of this burner assembly. So this particular part, the length of this thing is about 3.5 meters, and the burner tip that's being shown here, this thing would actually melt off over time. So this was a maintenance issue. So they'd have to take this part out, cut this off, and then braze a new tip on each time. And so obviously we have downtime, which is no good, especially in that type of, in the energy field. And so this is what he was tasked with, is to come up with a better design on this. And obviously the lead time on this is going to be pretty long because it's a bunch of machine parts that have to be all welded together. So here's where the fennel bulb comes in. So the thing about the fennel bulb is that he noticed that there was all sorts of veining and channels in this. And so he said, you know what if we took this design and we actually, I brought this to the burner. Now, obviously, this is something that from a traditional or conventional manufacturing, there is no way, as you can see this animation playing, no way that you're going to be able to do this traditionally. Just not possible. So that was the inspiration. So what he utilized is our CAE software, which is, we utilize a tool called HEEDS, which you can set the parameters for the particular part, and it will actually create the design for you. It'll optimize the design. So it'll go through and it'll check, to make sure that, in this case, the heat exchange is proper in optimizing that. And so, as you can see the chart and the scatter diagram over here. Here we go. The scatter diagram over here, which is actually going through, and it's automatically designing and running through the different iterations of the part, and you can tell it how many iterations that you want. You don't want to go crazy and let it run for 3 weeks, but you could if you wanted to, if you really, really wanted to optimize something. But that's what was used in order to optimize this part. So now we were able to bring this part down from 3.5 meters to 1.5 meters. So really we've reduced the entire size of this thing, as well as its own one part. And what's the other cool thing about this is, I'll go right here to the video. This actually disperses the heat better than anything that they would have had been able to design before. And this is the gentleman that you'll see. He was the engineer that designed or redesigned the burner. And as you can see, he's heating up the ring to prove a point, and you can see it's getting glowing red. And he's going to pull this thing away, and he's going to put his hand on it just to prove a point that how efficient this new design is to remove heat. So what's that done for us, for the customer in that area? This is no longer a maintenance issue. That tip does not melt off anymore because it's dispensing the heat properly. So that was a big bonus for us, and it also helped us win an additional contract. So these are the type of things that you need to look at, right? So it may not, when I mentioned before about cost and economics, you got to look at the whole big picture. So this was a little bit more expensive to make initially, but in the long term, it's paying dividends like nobody's business. Another thing that we did internally is in regards to our turbines. Again, the maintenance contracts is where companies like Siemens and GE and the likes make money, right? When it comes to energy, the less your turbine is down, the more money that you're going to make. So this particular part here, this burner, we call the Buma burner. This was made out of 13 parts. Took 26 weeks in order to manufacture this, right? And it's all machined, cast, forged, machined. and then it ought to be welded all together. And so the problem is this gets this combustion chamber down here gets to be about 1200 degrees Celsius, and so this tip melts off over time. So you have to constantly shut down the turbine and pull those out and then replace them. And so the first step was, well, instead of machining, and welding all this stuff for the tip, why don't we just weld a new, we'll grow a new tip, right? So we created a fixture and put it in the EOS printer and then printed a new tip on. That was the first step. And that worked pretty well, but they were still, melting off. Then the next step was, let's redesign this whole thing. And this is the redesign that you see here on the right-hand side. This has got conformal cooling channels all through the inside of these walls. So we went from 13 parts down to 1, 26 weeks lead time down to 3 weeks with a 22% weight reduction. I will tell you, we have no idea what the longevity of this part is now, because every time they shut down the turbines that we have out in the field and they pull these out to take a look at them, they look like the day they went in. Now you can imagine what that does for a bottom line. Just something simple like this, just this one part, right? Which was a big maintenance issue, no longer an issue. So again, look at the big picture, right? So in this case, we shaved off a whole bunch of time in from the cost of making the part itself, from this to this is huge. And now it's affecting the bottom line on the maintenance contracts, so it's great. It's great. So another area, I mentioned the Siemens mobility. So, it's not like we're making, thousands of high-speed trains. We're on the order of, tens of. And so instead of making molds now for these parts that are like within I guess they would call it the cab, where the engineer sits. Now we're actually printing those parts, which makes a heck of a lot more sense, because we're not making a bunch, we're not making en masse. So to get the money back out of, from a mold, or the payback from a mold, this is actually a lot more cost effective. Plus it's easy to make spare parts when we need them. We don't need to keep spare parts sitting on hand, right? So now if something breaks, that we've printed, we just print another one. So let me shift gears a little bit away from Siemens and talk about some of our customers. Toolcraft was one of the first folks to jump on board. Toolcraft does a lot of, builds a lot of molds for their customers. They do automotive, aerospace and defense, some medical device also. And I'll run this. I got a little video here, and hopefully we get the sound.
No volume.
One of the managing directors of our business is production of components, of assemblies by different production technologies. So just 1 year ago, we took the decision to start with the implementation of Siemens. The first step was the AM integration, and now we are about to integrate also the Sim Center portfolio. We are using FEM calculation, topology optimization, and also the AM process simulation. At the moment, we're planning the implementation of the MES MOM solution by Siemens. So the goal should be to be paperless along the process chain, and we want to collect useful data by the end of the process that we are able to submit a certificate to the customer with the part.
My name is Ralf Dumida. I'm the design engineer for additive manufacturing at Toolcraft. At Toolcraft, we have AM design challenges almost every day. Our customers send us the part, and our aim is to find the best solution for the customer. The benefits of Siemens NX are the consistent process chain which you can cover in the software. So we can start modeling, you can go direct to the simulation tools, for example, the process simulation, the topology optimization, and you can verify the result of your topology optimization by FEM analysis. Siemens NX cover all these different applications in one software environment. That's a huge benefit for the complete development process because you can save time and you can react to changes very quickly.
My name is Thomas Lender. I'm responsible for project management in injection molding and tool making. A big benefit for this manufacturing is the manufacture time from design to the first parts of tool. And the next benefit is simulation about cooling and mechanical strength, including the cycle time. We reduced the cycle time by 30% for this tool. The tool needs less energy for heating and cooling. It is easier to handle because it is lighter.
We always try to combine the benefits of AM technology with the functionality of the customer part. Therefore, it's absolutely necessary to work with a comprehensive software tool like Siemens NX.
2018 was definitely a very exciting year. We had huge expectations to Siemens. So far, I can really say they are completely fulfilled, but we have some topics to do, and we believe that also we will have the same quality of collaboration that we had so far.
So that was pretty innovative for them to focus in on the mold designs. So we're going to jump into a different area again, which is we call this the super duct example. And the video for this is pretty self-explanatory, but we actually were trying to come up with some projects that HP and Siemens could work on together, and something fell out of that had nothing to do with the original intent. So I'll let this video play.
Additive manufacturing works always from the application backwards, user-centric. If we're not helping customers visualize the potential of this new technology, it won't happen naturally. We came together with the new development from HP for the much more productive 5200 series system and the Siemens software solution.
A deadline is the mother of innovation. This started a few months before we launched the 5200, and that gave us a couple of months to come up with something.
So we got our teams together for a workshop in Vancouver, Washington, and we spent 3 days together, locked in a room. We talked about structures in an automobile that you could optimize for crash protection. We talked about cooling and batteries. All that while we were brainstorming, there was this unassuming cooling duct sitting in the middle of the table. Finally, one of our guys picked it up and said, "What is this?"
Of all the possibilities, we landed on a duct, which is part of our own HP 3D printing devices.
To maintain the reliability for that print head, we need to keep the ink cool, and that's done through the cooling system. The duct was an integral part of connecting the fans to the cooling of the pen. We already had a 3D printed version which combines 6 parts into one, but we wanted more. We wanted more performance from the general flow, and we wanted more balance between the 2 print heads.
Quality optimization will look at which parts of that design space help to gain our engineering objective, which is minimizing pressure loss, and basically then remove those parts which are detractors. We had a super large amount of recirculation, so basically the air is going in circles, losing a lot of energy. Now we have basically 4 distinct flow guiding veins, which take out the swirl and immediately force the flow to go straight forward instead of going in circles.
So it was really hard to wrap your head around that geometry when we first got it from Julian, just because it was so different than what everybody was expecting. So I had to take that geometry, smooth it out, create a thin walled part from that we could use to create the duct part. I mean, when you talk about how the original duct was designed, where a person had to manually make every radii, every extrude, every little feature on that part, with a simulation driven part, you don't have that. The simulation makes the geometry for you, and that is a much faster process than trying to design all that by hand.
As the design was shaping up, and it defied whatever everyone, including me, was expecting it should look like, with the tongue sticking out.
I was pretty stunned when I learned that the software predicted a 22% improvement in airflow.
22%? That seems pretty high compared to our baseline. But again, Siemens, they are the simulation experts. We had to go back to the physical world and actually test that new design is going to deliver more airflow.
Sure enough, when we went back and measured, the Siemens design duct improved the airflow by 22%, just as the software predicted.
On the other side, normally you need months to develop these, and here we have reduced the innovation cycle time by 75%, which is quite remarkable if you think about it, because it's not like you landed on a design. We landed on the most optimum design for that particular problem.
Getting the optimized design was just half of the battle. The next part of the challenge was transitioning that design into the AM factor where we could produce it at scale.
A lot of companies only have experience with lab-like environments. So they have 2 or 3 printers, they know how to operate it, but they actually don't know how it will look like if they ramp it up with more printers. We're able to show the full simulation up to 100, 200, 300,000 parts by utilizing a digital twin, and then start with different scenarios to optimize how to improve it. For the end state, with 300,000 parts, would need 36 printers and 6 workers. We can take an application with improved performance from the flow optimization, show that we can produce it in the industrial printing system, and this is unique in the world.
It kind of tips engineering on its head a little bit. Engineers no more should really be focused on the form and what the product looks like. They should be focused on what the product needs to achieve. We've got a part now that has done something that I don't think anybody else in the industry has done. And when you combine that with HP's ability to industrialize additive manufacturing with their printers, it's a really strong solution.
Interest in this type of solution has been outstanding, and not only in the automotive industry, but also consumer goods. Think about refrigerators, air conditionings, vacuum cleaner.
What I'm most fond of from this project is going into meetings and handing the duct to a CXO and having them hold it and be inspired by what was possible with additive manufacturing and generative engineering, and wanting to be able to find a way for their company to be able to repeat this kind of success.
So it was really cool here. So you see on the left-hand side, so this was the original designed duct that HP designed. And then they went through and of course they optimized it, right? So this is their optimized duct is one piece. And so they thought they were done, right? And as the video states, and we were able to, utilizing our tools, create something that was even more efficient as far as performances goes with the redesign. So this obviously helped from the side of consolidating parts, which was good, but then taking it that one step further and reimagining that duct. The other thing that we've done in association with the National Center for Manufacturing Sciences, NCMS, is we proposed a cloud-based managed design for additive environment, so that specifically, focusing on what the DoD, the Department of Defense, would like to do, is to be able to design anywhere and print anywhere. So last year we went to work, rolled up our sleeves, and we have put together the first ever solution that, again, that's cloud-based and managed by our team center. So that truly enables anyone to design anywhere and print anywhere. So this is something we're going to continue to work on with NCMS in partnership. And we've renamed this the Digital Proving Ground, because it's a place where any of the AMP members, which is MCMS is part of, we're part of, can come and they can actually utilize this environment and get familiar with the process and the tools and quite frankly, designing for additive. You've already seen a picture of this. We're kind of running out of time, but you saw that in the HP video, is also thinking bigger and out of the box. Again, when we look at additive, we don't look at it as an island. We look at the big picture. And so what we did here for EOS is we helped them design, using our tools, a production facility. So you have your material handling devices, just like what we did for HP, you saw in the video. We did the same thing here for EOS. And then lastly, I just want to kind of wrap this up by saying that, you know, we obviously we have a methodology that we follow. We have a consulting organization specifically for helping enterprises, with additive. But we have this approach is, you really need to understand and ideate, if you're going to go for additive, is to learn, create your vision, as I mentioned, and then you need to define and a pilot, right? So you have to identify what you're going to do, how you're going to do it, and what your investment, is going to be in it, and start a pilot. Start somewhere, but start simple, start small. Don't run out there and buy, powdered metals if you've never done anything before, if you've never prototyped, you're not even familiar. Start small, start simple, and so you get familiar with it. Grow your people, invest in your people, so that you start to build a culture that is really looking at thinking out of the box, right? And then, of course, it's got to be economical. I will tell you, your first iterations and your first venture, this is an investment. Don't go into this and say, well, I have to have a return on investment, in 6 months on this. No, this is not the type of technology. There's companies that I work with. A lot of companies realize that we're not going to be ROI focused. We're going to focus in on pretty much the art of the possible. Right? What things could we do? How could this help us in the future? It's an investment. You start to make some money down the road, you figure this out, and you're doing some production parts, whatever, fantastic. But, you need, this is the time, this is the moment in time to start to embrace, engage, and learn. And I want to tell you too, celebrate not only your successes, but celebrate your failures. Right? Because again, this point in time, failures are going to be as important and sometimes even more important than the successes, because you're learning. I had the pleasure to be able to go through a training class with the great Dr. Edwards Deming, and his whole approach was always is to understand your failures, right? And then be able to learn from that. Pick yourself up and then, learn. Come up with your theory and then validate your theory and then continue. So this is the time in order to do that. Make the investment and make the investment in your people. And then, again, scale. Once you start getting the hang of whatever area, if you're making tooling, if you're making fixtures, if you're actually doing reverse engineering for parts, you're making spare parts, right? Start small, get some small successes, and work your way up, right? And then the last part of that is digitalization is critical, right? Is embrace it, manage the process, manage the workflow, capture those learnings, right? So it's not lost. It's not between somebody's ears and then they walk out the door, right? Digitalization, workflow management is really key in moving this forward for yourselves and for your company. So with that, we got about 10 minutes left for any type of questions. Be glad to answer anything you might have.
Okay, Chris, so the first question is, are the robotic solutions utilized in any private networks?
I'm sorry, are the robotic solutions what?
Utilizing any private networks?
Well, it depends on how you're gonna connect these things, right? Are you gonna do a standalone work cell? Are you gonna do a serialized production type of thing? Are you, and then are you gonna utilize edge computing? You can, kind of the sky's the limit, basically. I know for us, we offer all the above. So if you want to leverage edge computing in the cloud, we can enable that. And we have security factors in place and firewalls to protect, your work cell on the shop floor. But I guess the long answer to that would be yes.
Okay, great, thanks. Next question. Talking specifically about metal forming in the automotive industry, do you see additive manufacturing as a viable replacement for traditional stamping press subtractive production model in the next 5 to 10 years?
Well, it depends. It could be like I think GM did a seatbelt bracket assembly. I think a couple of years back that they talked about, right? And it kind of falls in line with you have, might have been 3 or 4 different stamp parts that had to be welded together to create the bracket. And could something like that be replaced? Possibly. Again, scale is always a question. Stamping is so darn cheap. Let's say if you're doing like a cross member for a car, say, well, geez, I'm gonna lightweight that and I'm gonna make it additively. I don't know. It costs you pennies basically to stamp those out. Probably not. So what would probably be more viable is to say, like I mentioned, the body in white, right, versus a body in black scenario. You may replace it, but utilizing a different material, such as a carbon fiber composite. That's a possibility. I mean, again, it all comes down to the economics and scale. If I'm making a specialty vehicle and I'm only going to make 50 of them, then maybe I would do carbon fiber and print out the hood. Or
so
very parts, right?
Very volume dependent, I would say.
Yeah,
right?
Absolutely.
So there's another question regarding the types of materials that the Siemens solution supports, because I know this customer or this person's question is about, how do you keep tabs on all the new innovation and materials? What kind of materials are people printing in today from a metallic standpoint?
Oh my gosh. You name it, they're using it. Hastelloy, different variations of aluminum, Inconel. Oh my gosh.
Stainless steel too, right?
Pardon me?
Stainless steel too?
Stainless steel. So we keep a materials library, and then we've partnered with some companies to expand that. And I can't think of the names of the companies right now, but we have Team Center Materials Management. And within that, we have a whole host of library of materials that we can leverage. our additive tool has materials. So we pretty much support all the materials.
Great. This one, some additive manufacturing technologies do not require support structures. Is this a significant advantage?
Yeah, absolutely. I mean, when you can print something in zero space, like a Velo 3D or something like that, that's, but they all have, there's no, keep in mind, there's no one size fits all. They all have their particular applications where there's pros and there's cons. So you really have to understand that particular technology and how the materials react to that and what you're going to print. That's the key. So, it's not going to be, well, I'm just going to buy this printer and man, it'll do everything for me. No, that's not going to happen.
Okay, next question. Post-processing can be one of the most challenging parts of additive manufacturing. What are some of the new developments in this area?
So, by nature for us, I can only speak to, from a Siemens perspective, we've supported, machining subtractive for a long time, both from the hardware side of the house, from the controls, as well as the software. So that's one of the things I mentioned, that when we look at additive, we look at the aggregate, right? We look at the big picture. We're not just looking off in this, this little island over here. So, we were one of the first, we had partnered with DMG Mori on their hybrid machine, right? To be able to do additive and subtractive on the same machine. So, if you want to say, what are some of the advances, well, obviously, the DMG hybrid, and since then, others have come along, but that's one of the innovations to be able to do the two. And I'll tell you, with Multiaxis, you're going to see all sorts of stuff too, whether you have a work cell with two robots, one that's doing the additive piece and another one that's doing the milling, the subtractive portion of it, or whether you swap out heads. I mean, there's, strap on your seatbelt, because, we ain't done with this yet, right? So there's going to be a lot more coming.
Thanks. Next question. Are there any initiatives out there working on the additive manufacturing design for body in white with no welded components? And I think that was might be lead into the body in black discussion.
Yeah, I think you're going to see, especially, electrification with vehicles. Weight is a huge consideration, right? And composites play a big role in that. Even the ducting, right? So the example of the mighty duct, being able to cool the batteries, as well as the motors, and then the HVAC in the vehicles, right? So that's, you're gonna see different materials being used than what we're used to, right? For fossil fuel based vehicles.
Okay, thank you. So this one is more for looking for your opinion, Chris. So this one is 3D printing within the decision maker's mindset when they are sourcing tooling, prototypes, etc. Do you think they prefer a supplier that has 3D printers?
That's again, we're in this strange space. So right now, a lot of I would say most of the expertise for 3D printing is in the service bureaus, especially with metals. I could see the tier community, either one of the two things is going to happen, in my opinion. Either these service bureaus will continue to grow, and they will grow into the tier, the formal tier 2, tier 1 space, or the tier community is going to say, you know what, that's starting to erode some of our market share or our business capabilities. Either we're going to have to build it, or we're going to start acquiring service bureaus and bring that in-house. we've seen some movement in and out of companies, service bureaus being purchased, some intellectual capital being stripped out, and companies being, sold again. So there's, again, you're going to see a lot of movement in that space too. So it's either you're going to have to buy the knowledge or you're going to have to grow the knowledge, and growing the knowledge is going to take time.
And I think an important thing to add, Chris, too, is, a lot of the OEMs are actually starting this thought process, right? From an R&D perspective. So like you said, in composites and others. So that is truly occurring. So I'm going to just do our little wrap up here from, that was the end of the questions for now. So I wanted to talk a little bit about, how Tata Technologies and Siemens can support you. So we would like to consider this as an invitation for you to reach out to us. Tata and Siemens can work together to create a plan to help you innovate. Really what you want to do is we want to help. We are the thought leaders, Siemens and Tata, when it comes to manufacturing in the additive space. So we would like to help you create a vision and a plan to move forward. As part of that, we have educational support. We have a self-paced learning called I Get It. There's 300 plus hours, multiple courses on there. And then we also have instructor-led training. So those instructor-led training, recently we've been doing a lot of them over the web, but we can do them in person. Just to let you see what we have, I'd like to point you to the lower right corner. We do support training for CATIA, SolidWorks, PTC, AutoCAD, Autodesk. We have some unique engineering skills classes there, like GD&T, ISO fundamentals, injection molding, project management, vehicle design and packaging. We are planning on adding a self-paced course for additive manufacturing, so that's in the works right now. If you have, our call to action is next steps. You can reach out to Tata. Our website is right there, Tata Technologies, the Siemens link, or you can reach out to Karen. She's our marketing manager for Siemens, and we have links in there on Learning Advantage. We can also do trials on some products, and then we also have a lot of support around Team Center. We do benchmarks, PLM roadmaps, things like that. So that's really all I wanted to cover at the end. Chris, did you want to add anything? But we really appreciate your time and participation.
Glad to do it, and I hope that stirred some thought amongst all the participants.
All right, and I just want to say thank you to Chris and Steve, and also to the viewers today for watching. We hope you'll tune in for our next Tech Takeover on January 13th about cultural adoption of Industry 4.0 with Saddlewood, engineering and ergonomics and visual decisions. And just a reminder that this event and all of our tech takeovers are archived on our website for you to view later. Thanks, everyone, and have a great rest of your day today.